So today we're going to work on the Xfoil project. Part one is getting the CL versus alpha, CD versus alpha, CL CD versus alpha graph for these three airfoils. We're just going to work on one example for each part. So I'll just do the NACA 0015 for this part. We're going to go into Excel, into Xfoil. You're going to launch Xfoil. Let's see if I'm sharing Xfoil right now. Here. Let me share Xfoil. And then what you're going to do is going to hit NACA because they already have the NACA airfoils in their database. I'm going to put 0015 for the symmetric one. It's going to give me this. I'm going to hit PPA-R. What it's going to do is going to show up a screen of our panels. See if I can share it as well. Share for this. And basically, you're going to go back into you go back into the Xfoil, and we're gonna change the number of nodes. We're gonna hit N and you hit 250. Then you hit T and hit 1. Change the and changes the number of nodes around the panel. Because currently it's at 160, so now you're gonna change it to 250, and then T changes the trailing leading and panel density ratio. We're gonna change it to 1. Then we're just gonna hit enter, and then it's gonna update, and you'll see it in there. It'll present all the parameters, and then you hit enter again, and then we go back to Xfoil. So for this case, for our part one, we want to do it in a Visid flow. We want to do it at a Reynolds number of 1,000,000. So we're gonna hit oper, give you two operations. Right now, oper I says in Visid, but we'll change it to Visid by saying Visc. Then enter the Reynolds numbers of 1,000,000, and Mach number does not matter for this. It's analysis for Xfoil analysis. So what we're going to do next is change the amount of iterations we have. Right now it's at 10. We're going to change it to 100, just to have more accurate. Hopefully that it'll converge. And once you do that, basically you can change the sequence to polar if you want. Polar plus would be 0.8, or you can change it back by hitting sequence P again. Either way is fine. And then you're going to hit I believe it's PACC, which is going to make a file for with all the information of basically all the CLCD coefficients at each different segment of angle of attack. You're gonna plot this analysis against. So what we're gonna do is just save it as video part one. Hit enter and then hit enter again. And now we're gonna run the analysis, which is going to be ASEC. Then we're going to put it from -5 to 15 degrees in that one iteration. So we had first angles that we're starting at. The 15 is going to be the alpha that we're ending at, and then 1 is going to be the non iterations it takes there. So we're -5, -4, -3, and so on. And then you hit enter, and it's going to run this. I don't know if you guys can see this on my screen. I'll try to screen share it. As it's running, it's creating this. And it'll show you basically the CP values across of all the analysis. After it's done, we have all of this in here. We can go into our file and we can hit open Excel because it's going to point it as a text file. So we open Excel here. And we share Excel screen, sure. And so once we do it there, we go to here. And then basically we hit open in the file. We're gonna open the, where is it? That's gonna be called, oh here, it's gonna be called, well, let's see, give me this one, please. Hit all files, I think we called it video part one. We're gonna open this up. just next, finish. And now we're going to graph our alphas and CLs. The first thing we could do is just click these two, insert, make a scatter plot. Basically, it's going to, that's just going to be, and we could label it as, we could label it as the CL versus alpha. And then we can do the same for the rest of these. So you can just hit insert, scatter plot, left click and hit select data, add, write the series name. So this will be CD versus alpha. Then series X value, click this range. And then for this, you click, well, actually, I bet for this, you can click the alpha range, because that'll be your independent variable, and our dependent variable will be the CD. And then we hit OK. That's gonna be our CD versus alpha graph. Hit OK after that. And then what we want to do as well is create a CL divided by CD column. So that equal to, this is going to be B12 divided by C12. Actually, apologize, C13. So we'll get that value. We'll click it all the way through here. What we're going to do again is hit insert, scatter plot, select data, add. This will be the CL over CD versus alpha. And then we'll hit the, this is the independent variable, and this will be the dependent variable. And then we're going to have our alpha. It's going to show our alpha. And then in the project, what is the project asking for? It's going to ask for the slope of basically of the CL graph. It wants to know what this slope is. So what we can do is just hit for the slope. We could just set this equal to, we'll take the 0.5, and we'll take this 0.5, and we'll take the, this is the rise of a run from 5 to -5. So what we're going to do is set equal to B, this will be B at 5. So B23 minus B13, and divide that by A23 minus A13. And that will give us our slope. And the slope should be good, because it should be close to 0.11 in for terms of degree. So we know that's good, especially for symmetric. We know that's solid, so we know that we're getting something correct. And the next thing you want to do after that is get the minimum CD value. And now we just hit that equal to min, and then highlight basically the C13 through C33 row. And it's going to give us the minimum value as a 0.063, which happens 34, which is going to happen at this is going to happen at basically angle tag 0. So now we know that this happens at angle 0. And then we want to get the max CL over CD value, because this is going to tell us basically how well, or what point we want the optimal angle of performance, of aerodynamic performance. So we're going to hit max, and then put it for the H column. So it's going to be H13 through H33. Put that equal to, have that equal. And that's going to give us this value, which is going to be the optimum point of, it's going to be our maximum CL over CD value. And this is going to be at angle 9. So alpha 9, we'll put, should be alpha 9 angle, but it should be alpha 9 right here. So that explains everything what this project is asking for. Let me share screen for that. So basically, we've done all of this. We've done the maximum. We're going to get an alpha for the smart. Now we're going to move on to part 2, and this is where we're going to use the Clark W foil. We get a Clark W foil from the UIE airfoil database. It's going to give you a textile thing, and essentially you're going to have to flip the first chunk, invert it, because an X-foil reads from the trailing edge to the leading edge of the top part, and then from the leading edge of the bottom part to the trailing edge. So we have to flip it in there. But what you'll do for here is then go back into X-foil, and we can just exit X out of X-foil. It doesn't matter for here. And then here I'll share my screen. open. Here, I'm doing share. And so what we're going to do here is we're going to hit load. And we're going to use the exact file that we have. The file we got is a clarkw.dat, and make sure it's exactly correctly. What it's going to do is going to pull up the new panel. Here, I'll show that as well, which is going to be the pitlib. And then going back to the Clark W data, what it wants us to do, what we should do for part 2, if we're going to do that multiple different Reynolds number, just an analysis of it. So we're going to do the first one. We're going to do this one at envisted. So since we have this already, we're going to do PPAR, and we're going to change the nodes to 250. Actually, we'll change it to 350 for better results. And then T equals 1. Change, and that'll be all. Now that it's updated, yeah, it's updated. Now that it's updated, we can hit our opper, and then we can go to, if we're going to keep it invested, we keep it invested. So we can just keep it invested for this one. So that's good. We'll change our number of iterations. Iterations will put it to 100. And then we will basically do our sequence to P. That will just pull our part. If you want, then we'll do our pack, which is going to set the file number. So we'll do that to video part 2. Don't get rid of the spaces. Hit enter. Now we're going to do our ASEC from -5 to 15 of 1 iterations and run it. And it's going to be really fast just because it's an invested flow. So now we're going to go and open that file in Excel as well. Open. Video part 2, we hit open. And then we hit next, finish. And then we share. So share. Oh, sorry. Part 2 Excel. So now we have new data. What we're going to do is do the same exact graph that we did just the last time. I don't feel like showing you that yet because that's just going to reiterate. We know how to do that. But what it wants to notice now is it wants us to get the max CL. So we would hit equal max, and we'd highlight the CL one. So it's going to be B13 to B33. And that'll give us our max CL, where it's going to be our CL graph is going to be a maximum. And then we do that the same with the min for the CLD. So we're going to hit that min, and we'll do it for column C. So C13 to C33. And since it's an invested flow, it's just going to be 0. And it's not going to matter. And the same thing if our CLD or CD is going to be 0. So if we look into our Expo project, so let me share for that. Basically, you're going to get the CL maximum that way, just shows you the CAD min. You do the CMCDV unbiased and find the errors for that, like we just did in part 1, and you tally those results. If you want to look at the document I have right here, here is the results for, this is the results for, let me see. Let me share this too. If we go into here, you can see for part 2, this is going to be the CL versus alpha. We get a CL max, and then we're going to get is for laminar flow. And here's are the values of CL max we talked about, the alpha model for that. And then here's for turbulence as well, which is going to be it's going to look like these, and then you get these same values as well. Basically, it knows that as radial number increases, the CL increases, the CD decreases, and the CL over CD increases, and the alpha optimal pushes to the left. So for now, for part 3, what we're going to want to do, maybe I set up Xfoil, open up Xfoil again, and here we share. What we're going to want to do now is basically load back our Clark W like we just did. So Clark W dot dat. And now we have it back up here. And what I'm going to do now is change the geometric design of it. So I'm going to hit GDS. Right now, I'll show you. Let me share. It's going to pop up this window, and this window kind of just shows you like what we're going to share, what's going to be different with the what we're going to change. We're in buffer mode now. We're going to change the airfoil, add like flaps or hinges or flaps or slats onto it. So what we're going to do is add a flap at 10 degrees at the 0.7 mark. So here, let me go back to share. So what we're going to do is just write in flap, and then we will put this at 0.7. And then what we're going to do with this one is that we're not going to split it as wireframe, so we're going to do half the thickness. So we're going to set this to 9999, and half the thickness is 0.5. And then we're going to put this 10 degrees down. So now it has everything, and to have everything saved and everything, we want to hit X. That's going to be execute, basically our execute command. And now it has everything set for the buffer nodes. We exit out of there, we're back in Xfoil, and then we can hit our PPAR and change the nodes to 350, change the T to 1, and then hit enter again, and we should be good. So now our thing looks like this. It's basically what our new PPAR looks like, basically our airfoil or our after adjustments with a new C effect, court effective. So now we'll go back to Xfoil. And we're going to do Xfoil at 1,000,000. We'll put it in an embed flow. So what we're going to do is hit Opera. We'll hit, this is viscous. Our Reynolds number will be 1,000,000 again. And then what we want to do from here is change the number of iterations. For flaps, I suggest doing about 1,000. And then we can hit our sequence P, change it to polar. Then our pack, I'm going to put this to video part 3. And then our file name, we're done with that. And now we can actually do our A sequence from -5 to 15 to 1, and go ahead and go do that. And it's going to take a little bit longer because it's going to be at 1,000 iterations. And some angles with these flaps that are not going to work, so you have to kind of just go with it. The Xfoil should tell you what angles, basically, if you read through the data, like what angles it's just not going to converge at. So you may have to play around with that. And once you see in your data, and once you pull it up into Xfoil, you'll see which alphas like kind of don't work. Like I know for the 20-degree flaps, I know that like -5 doesn't work, -4 I don't think works, -2, -3 works, but -2 doesn't converge. So it just kind of like doesn't include that data into it. I think so. This one's done. We'll see basically how much data is into it. So let me go into Excel, file, open, browse. And I'll open the video part 3, open, next, finish. Here, and let me share a screen for that. So now we have all this data in here, and we're going to do the same CL versus alpha, basically plots. So I could just insert this into here. You see the same alpha plots. You're going to do this, all of that, and the project is going to make us do basically that for all of that with the C over CLD. Here, if I share with the Xfoil, yeah, it wants us to do with everything with the, and we do this with a 20-degree as well. You can do the same thing as a 20-degree. You just change that one part to 20 degrees. You might have to go up to like 450 nodes for that, or maybe different more iterations or whatnot for that, for it to converge to different parts. But you're gonna get the same alpha and CD, max, CD min, CD alphas, and you're gonna basically get the results for that. So if we go back to our video part 3, let me share that. We do that for this one, and then you're going to get your max from here, which is going to be 1.519 for our CD. Your max is, your lowest you can min is going to be at -1, which is going to be 0.0.7. And if you do CD over CL, which I'll just do that really quick, equal to, this is going to be what, B 13 divided by C13, and just tabulate that for all of these. I see our max is at 104, which is going to be at 0 degrees. That's going to be the angle of attack where our airfoil is going to have the highest aerodynamic performance. And essentially that's it for the project. You just tabulate all the results. Let me share this Word document, basically show you what it looks like. This is going to be the project. It's going to have all the graphs. Sometimes you can't see because it hasn't loaded from the Excel, but it's going to have all the information here. And like I was saying earlier here, let me show you down to these flaps. This is all the information but for the 2-degree flaps, for the 20-degree flaps, I can only get it to converge from -1 degrees to 15 degrees. So this is all I can get for that as well. And that's basically the whole project.